Alright, so in this lecture, I'm gonna be talking about another way that we can leverage this contrastive learning for tasks that we do in deep learning or NLP. Here we are using cluster analysis with deep embedding, and we enhance it with contrastive learning. This article in 2021. Because our motivation is that this k-means that people use does not scale well. So cluster analysis is one of the fundamental challenges in unsupervised machine learning and has been widely studied. In the context of computer vision, image clustering aims to group data without the presence of ground truth labels. While this task has been approached from different perspectives, data grouping is generally done based on some well-understood metric for measuring similarity, such as pairwise distance metric, distance between separated clusters. For example, the well-known k-means algorithm in 1967 assigns each data point to the cluster with the minimum mean based on Euclidean distance and iteratively refines this mean in the feature space. Although this works well for lower dimensional data, that doesn't scale well, and the choice of feature space becomes more decisive. Unsupervised disentangled representation learning is a long-standing problem in computer vision, but this work proposed a new novel framework for performing image clustering from deep embeddings by combining instance-level contrastive learning with a deep embedding-based cluster center predictor. Our approach jointly learns representations and predicts cluster centers in an end-to-end manner. This is accomplished via a three-pronged approach that combines a clustering loss, an instance-wise contrastive loss, and an anchor loss. So 3 losses. And our fundamental intuition is that using an ensemble loss that incorporates instance-level features and a clustering procedure focusing on semantic similarity, they reinforce learning better representation in the latent space. And we observe that this method performs exceptionally well on popular vision datasets when evaluated using the standard clustering metrics, such as this normalized mutual information, in addition to producing geometrically well-separated cluster embeddings as defined by the Euclidean distance. This is the model architecture that we have 2 augmented views of this one image. So we have 2 augmented views. 2 augmented views of one image are processed by F, which is your backbone, followed by GI, this GI, which is instance-wise contrastive head, for computing the instance loss. A raw input sample is fed to this backbone, followed by GC and GT for computing the cluster loss. So we calculate the cluster loss here. But the net, the sum of all 3 losses, the net loss is computing using the instance loss, cluster loss, and anchor loss, 3 different losses. For example, for instance-wise head, we choose a neural network that maps the representation to the latent space, where the instance-wise contrastive loss gets applied. We use the representations of the augmented data samples as the input to the instance-wise contrastive head. And this contrastive head aims to maximize the similarity of positive pairs while penalizing the negative ones. Formally, given a mini-batch of size n, we generate 2 data augmentations resulting in a mini-batch. And let x1 belong to BA be the first augmentation of the kth input sample, and xk be the second augmentation of the kth input sample, and we consider this one as a positive pair in the mini batch and the remaining examples as negative pairs. For the kth sample in mini batch, the backbone layer generates representations for a positive pair along with 2n-2 negative pairs. So the contrastive head takes the representations as input and producing these Z. And we choose 2-layer multi-layer perceptron with one hidden layer. So without loss of generality, we apply this loss. And tau here is an temperature parameter. And by the way, there is an article that focuses on the effect of this temperature on uniformity in alignment. So while the contrastive head brings similar instances closer, the clustering head maximizes agreement between semantically closer samples, thereby bringing samples that cluster together, resulting in compact clusters. And so, given k initial cluster centroids computed using k-means, we perform a two-phase parameter optimization. And we compute soft cluster assignment by using this student T distribution as a kernel to measure similarity between the embeddings h sub I and centroid mu sub j. And hi is fxi where xi denotes a mini batch, so it denotes a mini batch with unaugmented samples. And alpha here are the degrees of freedom, and qij is the probability. This is the probability of assigning sample I to cluster J. And that auxiliary target distribution, suggested by Ali Farhadi in Ali Institute for AI, he suggested to use this one. I have explained his excellent paper in a different video in a playlist for deep learning in 2032. And so we define our clustering objective. It's just a KL divergence loss between the cluster assignment and the target distribution. So it's just a KL divergence between the two. And to compute the net clustering loss, we compute L for all the samples in mini batch. And for anchor network, while the clustering loss brings semantically closer clusters together, it only performs parameter optimization over a mini batch that consists of raw image samples. We propose an anchor loss such that cluster assignments for raw samples explicitly maximize agreement with augmented cluster assignments using an aggregated KL divergence loss, and let the anchor distribution for the I sample be these, and while the Jensen-Shannon divergence produce a symmetrized and smooth version of KL divergence by considering the mixture distribution of two probability distributions, we pair an anchor distribution with two probability distributions that smoothens the combined KL divergence loss without changing the structure and symmetry of the objective function. So we compute the loss as these sum of these KL divergences. And to compute the net anchor loss, we compute this Li for all samples because we have n samples in mini batch B. And then we combine different losses that we have. We have 3 different hyperparameters. We can play with them. So it's a trade-off between 3 different objectives. And we use TSNE algorithm for visualization usually. And so you see that when the number of epochs goes higher and higher, you see you convergence, you can see the convergence and also evolution of the intercluster distance. The distance will be higher and higher, as you see, and then the accuracy and that NMI measure with for the CFAR10 dataset that we always use. So CFAR10, as you know, it has 10 classes. This one is more challenging. It has 200 classes. For performing a comparative assessment, we consider 3 metrics. We use normalized mutual information, accuracy, and adjusted RAND index for evaluating. But for these metrics, a higher value indicates a better clustering. So a higher value, it means a better clustering. So if you combine 3 different losses, it is better than you just combine just 2 losses, 2 different objectives. And this one is much better than just one objective. So the more objective you add, the better, the higher accuracy and NMI and ARI.